right, cool. Okay, so today and on Wednesday, I just want to give just maybe an overview of deep learning. Obviously, there's a huge field here, but I just want to cover the things that I think are essential that describe basically every deep learning model that you'll encounter. And mainly we're going to focus on when you want to use deep learning. Because it's so complex, we're going to talk a lot about how you can sort of probe it to figure out what it's doing. And then the big thing I'm going to cover, especially on Wednesday, is how you train large models, because there's some subtleties in how that calculation works that I don't think are necessarily obvious. And that'll be about as far as we'll go with deep learning, but Pankaj's textbook has an entire additional like 5 chapters on it if you want to go deeper into it. Okay, so I've spent a bunch of time talking about linear models, partly because linear models are surprisingly good, right? I think that for a lot of problems, it makes sense to try a linear model before you just throw a giant neural network at it. But the big limitation of linear models is that even though oftentimes with enough parameters, they're pretty effective for both regression and classification, as we saw with logistic regression, there are cases where you'll run into pretty clear difficulties. Okay, so what I've done here is I've created a really toy learning problem that basically just consists of fitting a model to 4 data points, each of which has a label. So this is going to be a classification problem where every data point has 2 features, which are going to be coordinates in an XY space. And then the label is going to be 0 or 1. And it turns out that if you look at this data set, it basically corresponds to the truth table for the AND function, where if my 2 features are both 0, it maps to 0 because nothing was on. If only one of my 2 features is on or is equal to 1, it still maps to 0. But if both of them are equal to 1, it maps to 1. So this is a very, very small data set where there's 4 possible inputs. The entire universe of possible inputs is just 4 distinct cases, 2 different values of the 2 features. And there's just one thing that turns out to be deterministically related to what these 2 features are. Okay, so this is a more modest problem than classifying the phases of the Ising model, because instead of an entire universe of 40 by 40 lattices of spins, there's only 4 possible data points in this entire universe, and it looks like this. Okay, so this is a data set implementing the AND function, and this is what it should look like. Okay, so if I have these 4 labels and I fit a linear regression model on them, there's probably no surprise that fitting a model on these works pretty well. So what I'm going to do is I'm going to take these four data points and I'm just going to fit a logistic regression model on. I'm using a logistic regression because I have only 2 output cases, 0 or 1, so I don't want to use linear regression here. I'm just going to use scikit-learn to do this. Great. And you can see that the predictions of my logistic classifier are that these are 0, that's 1. Looks like it did pretty well in this 4 data point example. Okay, so that's obviously not the most exciting output, but it's just that logistic regression is capable of expressing the function class corresponding to the AND data set. So this data set can be fully matched by just a straight linear model. Okay, so one thing that I can do to maybe try to probe what my classifier does is I can try to see how it would react if I gave it inputs that it wasn't trained on or wasn't tested on. So what I'm going to do here in the next cell is I'm going to take a bunch of different XY values that lie between these data points. So rather than just using 0, 0, 1, 0, et cetera, I'm going to give it like 0.5, 0.5, right? Or I'll give it all these points throughout this space. And the point is to see at what point the model goes from deciding to call things off to calling them on. So I'm going to take this data, this model, I'm going to try to extrude something like a decision boundary that tells me when it decides to switch from this to this. Okay, so that's all this code does is it just creates a regular lattice evenly spaced throughout this domain. And for every single point in that lattice is going to generate a prediction using my trained regression model. Okay. So if I run this, I get a plot that looks like this. And this is pretty common in classification problems. This is a decision boundary. And it just says that if I look at some portion of my feature space as a continuous space of inputs, it just tells me how the behavior of my fully trained model changes as a function of that smooth variation of inputs. Okay, so this more or less does what we'd expect. It apparently turns out that the logistic regression model makes the decision whether or not the output is 0 or 1 based off of some hyperplane. Really, it's a line here through my feature space. Okay, so there's no surprises so far there, but it's interesting that this continuous valued learning model effectively picks a threshold here. Okay, so maybe that's not super exciting. It turns out logistic regression can solve a 4 data point regression problem. Okay, so now I'm going to do the exact same problem again, but I'm going to use a slightly different data set, which is instead of implementing the AND function, we're going to use the XOR function, the exclusive OR function. Okay, so this is another Boolean arithmetic problem where it takes 2 inputs, which could be 0 or 1. And it's going to assign a single output, which is just also 0 or 1. But the truth table for XOR looks a little bit different, which is that it only gives you a true evaluation if only one of your 2 inputs is 1. So in other words, when both my inputs are 0, it doesn't do anything. When one of them is on, it says, that's great, gives me a 1. But when both of them are on, it actually gives me a 0. So this is different than normal OR, where this would be a 1. Exclusive OR only allows you to be 1 if only one evaluates to that. Okay, so on some senses, this is almost the same kind of problem as we just did. It's just that the output labels are a little bit different. Instead of this one being the only on one, only these 2 opposite corners are the ones that should evaluate to be equal to 1. Okay, so this is, in principle, another simple problem, right? It's only 4 data points, so it should just absolutely crush this problem. But if I fit a logistic classifier on this, something kind of weird happens. So here what I've done is I've plotted the predicted labels, and I've also plotted the decision boundary underneath them. So we're just looking at those 2 plots I showed above on one plot. So basically, the logistic regression function basically classifies everything as off. In other words, it can't figure out that it needs to have these 2 on, and so it gets 2 of the points wrong at all times. And this is kind of weird, right? Because, this is a linear model. This is 4 data points. It really feels like it should be able to figure this out. But somehow the logistic regression model chokes on this and isn't able to solve this problem. Okay, so this gets into, I think, a big idea in learning theory, which is that, I'm just looking around. Okay, yeah. Which is that my logistic regression model, there's no way that I could parameterize it such that it would be able to solve this problem. And the reason is because if I look at the form of a logistic model, do I have it drawn here? Okay, I don't have it. So logistic model, neutron, nice. So logistic model has the form something like theta dot x, where this is a 2-dimensional input vector, this is a 2-dimensional parameter matrix, and this is just some scalar. It turns out that the only thing that a logistic model can do is draw a hyperplane through your feature space. It's not capable of drawing any other sort of decision boundary. So you can see why that might be a problem here. Because if I have a logistic classifier and it's only capable of drawing basically decision boundaries that look like lines, because it can only parameterize feature space using a line, there's no line I can draw through these 4 points that will get this classification problem right? There's no way I can split them. No matter what I do, I'm always going to get 2 of the points wrong. So in other words, this model class is fundamentally incapable of expressing this decision. Okay, so this sounds like a really trivial insight, but this is actually was a big advance in learning theory, which is this idea that linear functions are incapable, sufficiently large linear functions can't model any decision boundary. I'm going to suggest that there are certain classes of models there are certain types of data sets that are effectively unreachable for certain types of learning model. Okay. So this idea that we have to use nonlinear models to fit this data set if we want to capture nonlinear decision boundaries, this is what motivated early work by Minsky on developing multi-layer perceptrons, which were the first type of well-known neural network that was developed in I think the 60s through 80s. Okay. So far when we were doing supervised learning problems, we've seen 2 classes of models, both of which were basically linear, right? We saw vanilla linear regression, that gives you continuous output. We saw logistic regression, which basically gives you discrete outputs. That's nice here. And then we talked about a little bit how we can think about a multi-layer perceptron as just daisy chaining a bunch of nonlinear regression models together. So multi-layer perceptron, instead of just doing a single nonlinear function, here we're using a sigmoid times some matrix multiplication, which is this inner loop. A multi-layer perceptron just feeds the output to another nonlinear loop. So you can almost think of this as like a chain of linear models that are compressed together. Okay, so if I draw a simple multi-layer perceptron, I can draw a 2-layer model. So the way this reads is that I do a linear regression on this inner loop. So I'm going to take my features, multiply them by some weight matrix that needs to be probably a 2x1 vector. I'm going to get some outputs. Those outputs I'm then going to multiply by yet another weight matrix, which I then feed to some other nonlinear operation. And as far as we're concerned, you can think of the nonlinear operation as just any sort of function that takes one number and gives you another number. Here I'm using a sigmoid, so this function looks something like this. That's x, and that's the y hat. But you could imagine picking a different nonlinear function. But for now, let's just assume we're using something like logistic. And I claim that this additional step where we have not just a single round of sort of fitting a matrix, multiplying it by the data, applying a nonlinearity, but we nest it twice. This solves this expressibility problem that popped up in logistic regression where a one-layer model wasn't able to solve this problem. Okay, so let's see if that works in practice. So what I'm going to do is I'm going to fit a model that has two weight matrices now. The first one is going to be applied directly to the features, and then the second one is going to be applied to the output of the first, effectively, logistic regression. So this model architecture is called a multi-layer perceptron. And rather than implement it ourselves, we're just going to use a built-in implementation, just like we did for logistic and linear regressions. Okay, so this is a scikit-learn. It's just called MLP classifier. It's a classifier because we have discrete output labels. And in order to construct this model, we need to specify how large we want these inner matrices to be. And we'll get more into what these are here, but importantly, this just captures that there's going to be two stages here. Okay, so I'm just going to use that classifier instead to see if I can solve this XOR dataset problem. Okay, so it has the same API as logistic and linear regression. It's just a different model here. And you'll notice that all I've changed is this line here where I construct the model. The fit and predict methods look identical here. Okay, so the predictions look pretty good. And if I plot the decision boundary of the multi-layer perceptron, it looks like it is able to solve this model. So in other words, having an additional layer in your multi-layer perceptron allowed you to capture a non-trivial decision boundary in your data set. Okay, so this whole idea that, you need to use deeper networks or have a hidden additional features in your data set or in your model class in order to express difficult decision boundaries. This is kind of the whole idea behind neural networks, is that in principle, if I have a neural network with enough layers, or where maybe I have a large enough intermediate step here, it's in principle possible to express almost any Boolean function in terms of a neural network. And this motivated a lot of the early work on multi-layer perceptrons. Is there's actually proofs that if I make some of these models large enough, I'll be able to express an arbitrary decision boundary for any function class I can think of. In practice, these proofs aren't useful because usually I'm limited by how deep I can make my model. I usually don't want to have, a bajillion of these operations. But nonetheless, it at least suggests that while a logistic regression has certain functions it fundamentally can't express, enough layers or wide enough layers in a neural network should be able to express very complicated functions. Okay. So neural networks you can think of as sort of flexible abilities to represent an arbitrary nonlinear function connecting your input data. This is in this case, my 2x2 feature space to your output data, which here is just a scalar label. And in the limit where the inner layers are arbitrarily wide, it can be shown, this is called Cybenko's theorem, that you can express any function. It's just that in practice, usually you don't have enough compute to make an infinitely wide network. Okay, and some of the theory work is linked on the syllabus here, but it was originally known that you could do this for a one-layer perceptron. So if I only had one inner step here, it's actually in principle possible to express any function. It's just very difficult because you don't have enough compute. But it was actually recently proved that you can use narrow functions here and just chain more of these operations. So you can make a very deep network and achieve the same universality. That was only very recently shown. Okay, so that suggests that maybe this is a good approach that this is a pretty flexible approach for data, because in principle, if I'm willing to burn enough compute, I should be able to represent any function. So I don't run into this issue like I ran into with the logistic regression on the Boolean function. Okay, so that's the basic idea behind why we would use neural networks. And in the case of perceptrons, which aren't necessarily that widely used these days, they basically give us these basically give us the basic intuition for how we would do much more complicated models. Okay, so if I have my model that looks like this, that's just, some matrix multiplication, some nonlinearity, another matrix multiplication, another nonlinearity. Sometimes you'll see people draw those out using what I call kind of a longhand notation, where they call the input space a vector space of input nodes, and then they call those inner matrix multiplication hidden units. So for example, if my first matrix multiplication is basically if I have a 5-dimensional input and it maps it to a 5-dimensional space with a 5x5 matrix multiplication, I would say that my first hidden layer, which corresponds to the output of this first stage here, that's what's called the hidden units, or the width of that hidden layer. So these units don't actually get used, because then I'll get multiplied by another 5x5 matrix to get some new hidden units. And then my last layer is where I'd pull that down to whatever dimensionality my output space is. So just like we saw with linear regression, where we tried to generalize it, I don't necessarily have a choice regarding my input dimensionality or my output dimensionality, but I have a lot of choices regarding these inner stages, regarding how wide I make these matrices, because I'm going to condense out over that index anyway. Okay, so this diagram here is equivalent to just writing, in this case, a 3-layer perceptron, where it looks like my input lives in a 5-dimensional feature space. My first matrix is a 5x5 matrix multiplication. My second is a 5x5 matrix. And my third is a 5x2 matrix that pulls it back down to a 2-dimensional feature space. So all of these crazy diagrams, it's not that popular these days to draw these in papers, but there was a period from like 2014 to 2018 where people would put these in their papers. All of this notation is just writing a series of matrix multiplications, where these connections are somehow drawing the matrix or something. Okay, so multilayer perceptrons, they might not be the most popular model these days, but they capture the key idea of neural networks, which is that I can't control this, I can't control that, but I can decide how wide to make the network, and I can also decide how many times I want to do these inner multiplications. And that basically just corresponds to function composition. And I argue that on the limit of arbitrarily wide or arbitrarily deep, you should be able to approximate any complicated function using this architecture, assuming you're willing to burn enough compute on it. Okay, so that's the basic idea behind a multi-layer perceptron. Is it's just a linear model that's nested with a bunch of other nonlinearities. If I actually try to implement this, I'm going to just try to implement this as just like a code version of this. Basically, it just consists of a series of matrix multiplications followed by nonlinearities. So if I have an untrained multi-layer perceptron, so this won't do anything because I haven't actually trained it, that would correspond to something that looks like this. Sorry, my cells are messing up today. All right, cool. So the forward pass, where I could take this inner input data set and map it to an output, basically corresponds to taking my data, multiplying it once by a matrix, so that's this inner thing, applying an element-wise nonlinearity, so this doesn't change the dimensionality. I then take that output and I feed it to the next thing, so this next evaluation takes this output, multiplies it by my next wave matrix, gives me a new output, rinse and repeat. So this diagram, this function composition notation, and this code here are all equivalent. This is just the code version of function composition. Okay, so the reason I show this is because of this idea that when I compute the forward pass, or I actually try to make a classification with a multi-layer perceptron, I basically take a calculation and I take the output of that calculation and I feed it to the next step. And then I take the output of that and I feed it to the next step. So it has this very hierarchical structure when I do the forward pass. Okay, so here, if my input shape is a 10,000 by 5 matrix, so let's say I have 10,000 data points, each of which has 5 features. The multi-layer perceptron, when I evaluate it, it'll do all these matrix multiplications. And because my last matrix had dimensionality 5x2, I'll get a 10,000 by 2 output. So the hidden dimensionality completely vanishes from this function class because it basically is a choice I make regarding how wide I want to make these inner layers. Okay, so the big idea with multi-layer perceptrons is depth is just how many of these hidden units I have, or how many of these hidden operations I have. So that sets the number of lines that look like this. Width is basically just how wide these units are. And I can make that as big as I want because it's going to vanish when I do this matrix multiplication. So like if I wanted to, I could make this 50 or something. And this function should still run because all of this just gets contracted out. Okay, so that's width and depth. And then for my nonlinearities, I just chose to use hyperbolic tangent, but oftentimes it doesn't really matter what nonlinearity you use here. Okay, so for logistic regression, the activation function we used was a sigmoid, where we did our linear regression. We fed it to this element-wise nonlinearity, and that basically squeezed it to the interval that mapped to our, in this case, two classes. People use a bunch of different kinds of nonlinearities for different kinds of models. In a lot of historical work, as well as things like hot field networks, people basically used a step function. So whatever might the output of each layer was, you would just smash it to be 0 or 1. In a lot of more modern works, you'll see that people are starting to use these ReLU functions. So these functions, instead of having this form where they smoothly go between 0 and 1, they actually go between 0 and infinity. So they basically just zero out everything that's below, that's negative. There's some theoretical work on why these work better, but for our purposes, it's just important that this function is nonlinear. That's the key thing that makes it not possible to reduce this down to just one big matrix multiplication. And I'll mention that there's a couple of theories for why the deep learning boom happened. It all can be traced to this 2012 paper that used convolutional neural networks to classify images very accurately. There were a couple of innovations in that paper. One of them was the use of GPUs that ended up being very big for deep learning. But one of the other innovations introduced in that paper is they used this nonlinearity instead of this, which is what a lot of people before were using. It turns out that this nonlinearity, for sort of very specific reasons, ends up being much more effective for training neural networks. So that 2012 paper that set off arguably the deep learning boom, the inner layers of that network they were using were just this, with this as a nonlinearity. And those are called the fully connected layers. Okay. And Pankaj's book has a little bit of speculation about the different kind, or a little bit of analysis of when you might use some of these other nonlinearities. And these have various properties that are beneficial or not. But that often comes up in training, which we'll talk about probably on Wednesday. Okay, so that's a multi-layer perceptron. It's just a bunch of linear regressions nested with element-wise nonlinearities. Okay, so we already saw that, for a really simple problem or simple seeming problem, having this additional layer and this deeper structure got us a little bit more powerful model. But we're going to be able to see the power on that on a problem that we think is going to be a lot harder to do with a linear model. So the problem I want to demonstrate this on is predicting the Reynolds number of a turbulent flow. So you recall that I think it was in homework 2 that we implemented PCA and we applied it. We implemented PCA and we applied it to a flow field corresponding to the wake from a cylinder as a flow moved past it. And one of the things that popped out of that data set is that as we increase the speed of the flow, it becomes a lot more turbulent. So we're going to use that data set again, and I'm just going to excerpt that data set so we have slightly smaller input features. So I'm going to load this data set. I think this cell is kind of slow to load, so I won't rerun it. So all this does is it reads that same data set from the homework. It downsamples the data a little bit, and then we're just going to plot for each of those different Reynolds numbers a couple of example flow fields. Okay, so from that data set from the homework, you'll recall that when the Reynolds number was low, that corresponded to very slow flow speeds. And so the flow is very ordered there. It basically showed a train of vortices that were very similar to each other. And technically, this data set's a time series. So if I wanted to plot all of these, I would see these vortices gradually sort of move back in time. So that was my low flow speed condition, was this low Reynolds number case. And then as I increased the Reynolds number, which corresponded to basically different simulations or changing of control parameter, I started to see this vortex field got a little bit more disordered. And then when I got to really high Reynolds numbers, you can see that the vortices are kind of all over the place. Okay, so my data set, I'm going to think of this as a regression problem where, given just a picture of all of this vorticity field showing like what the flow looked like, can I guess what the underlying Reynolds number of that flow was? In other words, can I guess how fast the flow is moving past the cylinder based on how chaotic this field is? I mean, you can see why this might be easy to do, because if I just look at the low Reynolds number case, it looks pretty ordered. So I could probably look at that and say that looks like that's probably the 300 case. But when I get to these higher Reynolds numbers, you can see it's a little bit harder, right? So maybe you can kind of see that this is the 600 because the vortices are paired more. But then the 900 versus 1200 case, these are technically very different Reynolds numbers, but they just look, chaotic to me. I don't see any obvious structure in this that's not in this, or vice versa. So if I just look at my data, so I'm going to guess a priori that like the low Reynolds number one should be easy to classify, and that as I go to higher Reynolds numbers, it might be more ambiguous what's what for the model. Okay, so this is what my data looks like. So every input is going to be a bunch of pixel values that just say what the vorticity was at every point in the field. And then my labels are just going to be what Reynolds number the simulation was performed at. Okay, and I've already loaded that into memory because this cell takes 30 seconds to run because it's a relatively big data set. Okay, so just like we saw with PCA, as well as when we were doing linear regression on the Ising model, my feature space here actually has it actually corresponds to multiple dimensions of my input data points. So each of these is basically a 127 by 127 image. But because we want to use this for machine learning, we really want to flatten that to a space where all of the features are stored in the same index. So the first thing I'm going to do is I'm going to take every single one of these images, and I'm just going to flatten it from 127 times 127 shape to basically a giant vector that has 127 squared elements. So this is the same thing we did for PCA. We're just doing it here for each snapshot in this turbulence data set. Okay, so if I run that, I think I can rerun this and it should be fine. Yeah. I had 2,127 by 127 images. I flattened them to 2,000 super long vectors. And then every single one of those vectors has its own label where that label corresponds to the Reynolds number that simulation was performed at. Okay, so I have this giant data set and I want to get a sense of whether it's possible to, given a picture, guess what the Reynolds number was. Very similar to what we were doing a few weeks ago where we were trying to guess energy given microstates. Okay, so before I just throw this into some fancy machine learning model, the first thing I might want to do is try to feel out how different my input data sets are from one another. So before I actually try to fit a classification model on this, the first thing I'm going to try to do is just take the raw input data and apply some of these unsupervised learning techniques to it, just to get a sense of what that data looks like in a lower dimensional space. Because when I look at it here, I can kind of by eye see that maybe there's some patterns that differentiate these classes, but using unsupervised learning is a way to basically see whether these patterns are robust when I use decomposition methods. Okay, so I'm going to set aside these labels, this giant vector of 2,000 Reynolds numbers. I'm going to set that aside for now. And I'm just going to take my input data and throw it into PCA just to see what happens. And you remember that PCA is an unsupervised algorithm. It just takes vectors and gives you lower dimensional vectors. Okay, so that's what I'm going to do first. And then I'm going to compare the PCA to the labels to see how much of the structure is just purely captured by the PCA. Okay, and I think this is slow to run. We'll see. All right, we're going to do it this way. Okay, we're good. Okay. So what I've done here is I've fed each of those 2,000 by, or I've fed each of the 2,000 vectors, each of which has 127 squared elements. I think it was like 16,000 elements. I fed that into PCA and I've said to instead give me 2,000 two-dimensional vectors, which I can visualize in a plane. So I've taken my input data and I've embedded it. And then because I happen to already have labels for the Reynolds numbers, I've colored the data points by their Reynolds number. Okay, so when I do that, I start to notice something that I think kind of makes sense, which is that if I just take my data and embed it in this two-dimensional PCA space, my low Reynolds number data looks like it basically forms this outer circle. It's not great contrast on the screen, but it's sort of this dark purple color. So all of those points basically embedded together in basically a limit cycle in PCA space. And then as I went to higher Reynolds numbers, I kind of started to overlap a lot more. And then the super high Reynolds number cases are kind of overlapping with each other. So in other words, it looks like in PCA space, which is purely a linear transformation on a vector consisting of each of these pixels, it looks like it basically is able to separate that first class from the others. And that kind of makes sense because if I just look at these pictures, this sure looks like low Reynolds number, but these are much harder for me to tell which Reynolds number it was at. So it makes sense that PCA would basically be able to get the outer case. This also is pretty consistent with what we saw in that homework assignment, where we found that PCA on the low Reynolds number flows basically was a limit cycle because it turns out that it's effectively a periodic system. But then you get to higher Reynolds numbers, it just looks chaotic because there's no periodicity. Okay, so this suggests that my features are separated linearly when it comes to the lowest Reynolds number case, but the others start to overlap with each other. Okay, so that's already good enough to suggest that this might be an easy enough problem that we could solve with machine learning because already PCA is basically pulling this apart without actually training anything. Okay, so just for fun, we talked about PCA is basically a linear embedding. So it pulls you from this 16,000 dimensional feature space down to a two-dimensional space. But we mentioned that rather than using a linear transformation, there's all these fancier methods that have come out the past couple of years that basically do nonlinear transformations. So I also tried training a UMAP model. And UMAP is basically, you can think of it as like a nonlinear PCA where it tries to find some new low-dimensional embedding that preserves local structure. Okay, and the actual nuts and bolts of how UMAP works is, I think, beyond the scope of what I think I understand well, but you should just think of it as a nonlinear PCA. Okay, so UMAP, when I run on this data set, it actually looks like it's able to pick up very systematic differences. And that's because I just gave it all of these data points. The data points are shuffled, so they aren't even in order. But nonetheless, it's able to find some relationship in feature space where when it embeds it in lower dimensions, it basically pulls these out and separates them from each other. So this is a good sign because it suggests that there's some structure in this data that a powerful dimensionality reduction algorithm like UMAP is then able to pull to some space where it looks like these different flow Reynolds numbers are well separated. So this is just that there's some structure in this data set that is available to learn because an unsupervised learning algorithm just pulls out the structure. Okay, so that's the first thing UMAP does is it looks like it pulls out something that separates the low Reynolds number case from the high Reynolds number case. And it looks like these two intermediate cases are a little bit harder because they overlap more, but nonetheless, they look pretty well separated. The other thing that's very clear from the UMAP space is that in the UMAP space, all of these different snapshots, which I just gave to it in like a random order, they basically got embedded together as lines. So that happens sort of in the PCA case, but you can see that these points are separated, so they are discrete points. But here in the UMAP space, they're overlapping, so it basically looks like a line. The reason for this is because the points that correspond to this data set are a little bit different than my easing model simulations that we were doing a couple last week and the week before, because these points actually aren't independent of each other. So each of my data points is actually a different frame from a video of this flow evolving, which means that there's actually some continuity in my input space where each input data point has some other input data point that's super close to it. And this is generally true of time series, is that you have some continuity across your inputs, which is manifest in when you perform the embedding, you see continuity in the embedding space because two frames that are really, really similar to each other get embedded together. But what's cool about this is that UMAP doesn't know about time. It just tries to find some metric that preserves nearest neighborhoods, and it naturally ends up finding that some of these are trajectories. And some of them are not trajectories, so it actually separates the different videos from each other. Okay, so that's a good sign because that suggests that UMAP is, a pretty powerful algorithm. It's able to pull these things apart, and it suggests that we have some hope that some very fancy model trained on this should be able to predict whether a data set is turbulent or not. Okay, so far I've just been fitting models that just take the input feature space, and I've just been using the labels as a way to check what that featurization looks like. Okay. So I'll skip this for now. Okay, and I'll just mention, for this notebook, just for fun, I tried doing a bunch of other transformations. So rather than just taking the raw pixel values here, I tried taking the Fourier modes as well as a couple of other transformations, very similar to what we did on Wednesday. And it actually turns out that taking Fourier modes made this problem a little bit easier, but not much more than just taking the raw pixel values. So we won't get into this, but you can also perform some feature engineering if you want on this problem because it's a flow data set. Okay, so now that we know that this data set looks separable, we can try to train a model that's able to take an input image and predict the Reynolds number. And there's some reason to suggest it's possible because it looks like a PC or UMAP was able to pull it out. Okay, so I'm going to start by doing logistic regression, so linear model, just to see how well that does as a baseline. I'm going to emphasize doing this because I think it's often tempting to immediately just reach for, a neural network or something, but it's always good to have a sense of how well you'd expect a naive model to perform before you use some crazy model. Okay, so I'm going to do a logistic regression, and because we're doing supervised learning, I need to make sure that I do a train test split. So rather than doing this manually, I'm going to just use a built-in function in scikit-learn that takes your data and automatically randomly selects, in this case, 40% of it to be held aside for the test. So this is basically like a helper function that just does the train test split for me. And remember, I'm only going to do my fit on the training data, but when I do all of my evaluations of my model performance, I'm going to use the testing data. That's going to allow me to avoid overfitting, or at least detect overfitting. Okay. So I think that this hopefully, okay, so that trains pretty quickly. Good. Um, that's not right. Hmm. So got a perfect score, but I don't think that that's possible. So I think that my notebook I made a when I was running it I might have loaded something wrong. Red, red. Ah, got it. Huh. Um, I'm gonna do it this way. So I think that I've ran that notebook before class, and I think I loaded something that I shouldn't have loaded. So this is called neural networks overview. Let that cook a little bit. Okay, yeah. So when I ran this, I was getting this looks more accurate. So let me zoom in on this. Sometimes because IPython notebooks don't force you to evaluate things in order from top to bottom. If I run something downstream and it overrides a variable and I'm not being careful, it'll cause some problems. So it looks like I did that. Okay, so when I ran this, if I ran this correctly, when I run this logistic regression model, I get about an 88% score on train, and then I get a lower test accuracy. And this is actually what I expect to happen, which is I should always get a lower test accuracy than train, because train is possible to, it's almost always possible to get 100% if I'm willing to throw enough data at it. But the testing really tells me how well my trained model is able to generalize to things it hasn't seen before. Okay, so logistic regression is a purely linear model, but it actually does surprisingly well, right? This is probably better than I would do if I just looked at a bunch of pictures of turbulent images and tried to guess the Reynolds number. But what's interesting is if you look at the confusion matrix on this, you can start to see that it basically matches our intuition, which is that the number of correct classifications of low Reynolds numbers is super high, right? So there's a very high diagonal element there. But as I go to the higher Reynolds numbers, I start to get these off diagonal terms. So that means that a lot of the things that had a Reynolds number of 600 got misclassified as 900. That's what that sort of non-zero value means. And then the other bright value is just that there's similar sort of misclassifications here. Okay, so logistic regression does a pretty good job. But once we get to higher Reynolds numbers, just like me, it starts to have trouble. Okay, so the fact that this is possible and that it gets the bottom case super well, this is more or less what we expected to happen, both by looking at it by eye, but also by looking at the PCA. Because when we ran PCA, which is also a linear unsupervised model, it looks like it separated this one, and then these guys were all separated. So logistic regression more or less matches our intuition for what a linear model should do, which is splits this class, but has a little bit of mistakes when it gets to the higher Reynolds numbers. Okay, so now that we know that logistic regression has some limitations, but does pretty well. So now let's see what happens if we do a multi-layer perceptron. And I'm a little scared of what's going to happen now, but let's see if this one is able to run. Okay, that looks more accurate. Okay, so this is working. Okay, so the multi-layer perceptron, it gets an overall higher training and test accuracy. So training doesn't necessarily mean anything. It just tells us something about whether our model is expressive enough. But the test accuracy is only slightly lower, so I don't have that much overfitting, maybe 2%. But importantly, these numbers are bigger, especially the test. So it looks like the MLP, due to having this nonlinearity, is able to do a bit better on this problem. Okay, so that's nice, but it looks like the way that my multi-layer perceptron did so well was really by focusing on getting the lower Reynolds number cases well separated, right? So it looks like it basically perfectly got the low Reynolds number case separated, so all of those are correctly predicted. And then the 600 Reynolds number it also did a little bit better on. Uh, okay, so that's good, but it looks like the price I paid is that it actually started to have a little bit of trouble where it would misclassify the really high Reynolds number as 900. So in other words, interestingly enough, my model actually has a few worse values on its confusion matrix. It just has an overall higher accuracy on this data set. Okay, so that's nice. And that's just that this nonlinearity is, getting me something because I'm able to get a slightly better model by adding this additional term. Okay. So the nice thing about being able to use neural networks is that unlike logistic regression and linear regression, we actually have a lot more choices that we can make in how we structure those networks. And the fact that I'm not able to get perfect training accuracy, it's just that maybe I could afford to use a slightly bigger model for this. Okay. So my logistic regression, I'm stuck, right? Because that parameter matrix is equal to the dimensionality of the data. So that's however many pixels this is. But here I can make some choices in my architecture to maybe get a better performing model. Okay. So in my multi-layer perceptron, there were a couple of choices I could make. So if I go back up to the model formulation, um, I'm stuck in terms of my input dimensionality, my output dimensionality, but I'm free to make these layers as wide as I want. And I'm also free to have as many of these layers as I want. It's just additional compositions when I do my forward pass. So what I'm going to do is I'm going to try searching a huge range of different model architectures, which have different depths as well as different widths, to see if I can get a much better result on my logistic regression or on my turbulence prediction problem. Okay, so in order to do that, I'm going to set up a grid search where I'm going to search all possible combinations of models that I'm going to try two 3x3 models. This is going to be two layers, each of which has 3 hidden units. I'm going to try having just one hidden layer, which has just 10 hidden units. And I'm also going to try a deep model that has 3 layers. So each of these basically is going to define a different set of hyperparameters that define the structure of my neural network, where this is the deepest one because it has 3 layers. This is a shallow one. But conversely, this is the widest one because it has 10 units in width as opposed to just having 3 or 5. And what I'm going to do is I'm going to fit a model on the training data for every single one of these hyperparameter combinations and see which one appears to give me the best training accuracy. I'm then going to take the best model and see if that's able to get a better confusion matrix than this 92% accuracy case. Okay, so it looks like this took 47 seconds to run on my computer, so I won't rerun it live. But if I run all of these models, scikit-learn will basically search every single one of them. It'll do some cross-validation to avoid train test splitting. And it basically spits out that the best model that it found was the case where I use a single wide layer. And when you use the case where you have a hidden layer perceptron with 10 hidden units, it's basically able to get a 99% test accuracy. So it looks like the only misclassifications were at this point here. It's a little hard to see the color there. Okay, so that's a good sign. It suggests that if I'm willing to search around in model space, I'm able to do a little bit better on this problem. And it's just that here, for this particular case, I got a little bit better model by going wider rather than going deeper. Generally speaking, this isn't always the case, right? The choice of architecture and how it affects the expressivity of your model, there's whole lore about when you should do which. But usually speaking, in a modern setting, rather than committing to a given model architecture, you just would pick a bunch of candidate architectures, search across all of them, and just pick the best one using appropriate cross-validation methods. Okay, so that's picking my best model. And if I go ahead and run that on the full data set, it should go quickly. Yeah, and it looks like I got my confusion matrix right. Okay, so unlike logistic regression, where I had basically no hyperparameters to tune, I didn't have any choices I could make with the architecture. With a neural network, I have some choices I can make with the architecture. However, I have to be careful not to just overfit using those choices. Okay, so that's really nice. But then we can actually close the loop and we can say that, okay, we have this super good model that can basically take any one of these images and tell you what the Reynolds number was, which is probably better than I could do if I used my eyes. Is there a way to maybe take that and get out something like a decision boundary for the model's input space? So the decision boundary for this model is a lot more complicated than we were doing for the Boolean function case, because in the Boolean function case, we only had 2 inputs, so the decision boundary was a plane in a 2-dimensional space. In this case, our input space has dimensionality of 16,000, so it's not necessarily as obvious what space we plot the decision boundary in. So in this case, it comes in handy that we did this embedding, because rather than visualizing the decision boundary in the full dimensional space of all possible 16,000 pixel images, we're going to instead visualize the decision boundary in these low dimensional spaces that we constructed earlier. Okay. So what I'm going to do is, I think I already fit Yeah, okay, I already fit this. Because my logistic regression had a problem, I'm going to go back to this notebook just for safety. Um, okay, so I ran this UMAP model, and we saw that the UMAP model, when I used the actual ground truth labels, it more or less got it perfectly right. So we hopefully our classifier will recreate this correct label structure. Okay, so this is our true space where the colors correspond to the true Reynolds number. So if I take my logistic regression model, I'm going to give it every one of those input data points, predict the label, and then see what that looks like. And you can start to see where it starts to struggle. So the logistic classifier had 86% accuracy, so most of these labels are correct. But you can see that the misclassifications are when it was getting proximal over here. And maybe that is something like it was close in the high dimensional space. When I pulled it down, it's less obvious here. So my decision boundary, I can view it in the embedding space and start to see where these misclassifications occurred. Okay, so my unsupervised learning can be used to visualize decision boundaries. So if I then take that method and I apply my fancy multi-layer perceptron, then I see that I basically get the labels perfect. So this looks exactly like the ground truth. So in other words, I can use dimensionality reduction as a way to view what the decision boundary looks in a reduced order feature space. In this case, is this two-dimensional UMAP embedding space. And I can see that my model basically looks exactly like it should just by comparing the ground truth labeling to my predicted labeling. Okay, and this idea of sort of thinking of the outputs of your thing as labels to color a plot, this is sometimes known as pseudo labeling, and it's a whole thing for cases where you have data sets where you have incomplete labels. Okay, I'll go ahead and wrap up there. Thanks.